Hello viewers, in today's class we are going to discuss yet another important problem from integrals, right? So in this class we'll solve this important integral using the concept of beta function, right? And beta function is also known as Eulerian integral of first kind, right? So we'll see a very beautiful application of beta function, how to evaluate this type of integrals, right? So let us start. So let us call this integral as I, right? So here we have the integral 0 to pi x square divided by square root of pi minus x dx, right? So here what we will do, we'll first make use of the method of substitution, right? So what we will do, let us first take in the denominator, we'll take pi as common, right? So we have pi 1 minus x over pi, right? So this is the first step. So now we can write it as 0 to pi. Here we have x square, and we can take square root of pi like this, and then we have square root of 1 minus x over pi, right? Okay, now let us rewrite this integral as 1 over square root of pi, and then we have 0 to pi and x square, and let us take this term to the numerator. So we can write 1 minus x over pi raised to minus half, right? Because this is square root, this is 1 over 2 power, so we can take it to the numerator. So this is minus 1 over 2. So now let us make the use of substitution method, and let us take y is equal to x over pi, right? So we'll take x over pi as y. So this implies that x is equal to pi y, right? And here we see that the value of x varies from 0 to pi. So we have x is equal to pi y. So dx is equal to pi dy, right? And we can change the limits accordingly. So when x is equal to 0, then the value of y can be obtained by taking x is equal to 0 in this relation. So we have y is equal to 0 over pi, that is equal to 0. And when x is equal to pi, then we have y is equal to pi over pi, that is equal to 1, right? So when x goes from 0 to pi, y goes from 0 to 1. So now we can rewrite this integral in terms of this variable y as 1 over square root of pi. Then we have 0 to 1, and x can be replaced by pi y. So we have pi y square, and then we have 1 minus y and raised to minus 1 over 2, and dx can be replaced by pi dy, right? So let us arrange the terms here. So we have 1 over root pi, and see here we have pi square, and here we have pi, right? So pi square times pi is pi cube. We can take pi cube outside the integral sign. Then we have 0 to 1, and here we have y square, and then we have 1 minus y raised to minus half, and here we have dy, right? So now let us again rearrange this integral. So we have I, here we have pi cube, here we have square root of pi, which is pi raised to half. So now we can write pi raised to 3 minus half, and we have 0 to 1. Y square can be written as y raised to 3 minus 1, right? Because 3 minus 1 is 2, and here we have 1 minus y, and here we have power minus 1 over 2. The exponent is minus 1 over 2, that is the half minus 1, right? So we have written this integral in this form because we are going to use the definition of beta function, right? So the beta function is defined as beta mn as 0 to 1, that is x raised to m minus 1, 1 minus x raised to n minus 1 dx, right? So if we compare this integral with this one, then we see that the value of m is equal to 3 and the value of n is equal to half, right? So n is half. So now we have I pi raised to, this is 3 to the 6, 6 minus 1, 5. So we have pi raised to 5 by 2, and this integral is now written as beta, and here we have mn. So m is 3 and n is half, right? Now let us make use of one important relation between beta function and gamma function, right? Now see, beta of mn is defined as gamma of m multiplied gamma of n divided by gamma of m plus n, right? Where m and n are both greater than 0, right? So here we have m is equal to 3, n is equal to half, and 3 and half are both greater than 0, right? So now due to this relation, we have pi raised to 5 by 2, and here we have gamma of 3, then we have gamma of half, then we have gamma of 3 plus half, right? So this is pi raised to 5 by 2, gamma of 3, gamma of half, and here we have gamma of 5 by 2. Sorry, here we have 3 to the 6, 6 plus 1, 7, right? So we have gamma of 7 over 2. So now let us write the values of gamma of 3 and gamma of 7 by 2, right? So gamma of 3 is equal to 2 factorial, right? Because we know that gamma of n plus 1 is equal to n factorial when n belongs to the set of natural numbers, right? Or when n is 0, then we have gamma of 1 is equal to 1 factorial, that is 0 factorial, that is equal to 1, right? So using this relation, we have gamma of 3 is equal to 2 factorial, which is equal to 2, right? And using an important relation, that is gamma of n plus 1 is equal to n times gamma of n, we can write gamma of 7 by 2 as 5 by 2 times 3 by 2 times half, and then we have gamma of half, right? Due to this result. So now this integral I can be written as, here we have pi raised to 5 by 2, gamma of 3 is equal to 2 factorial, and here we have gamma of half, and in the denominator we have gamma of 7 by 2, and due to this result, gamma of 7 by 2 is equal to 5 by 2 times 3 by 2. Here we have half, then we have gamma of half, right? So we know that gamma of half is equal to square root of pi, right? So these two terms get cancelled. So now we have pi raised to 5 by 2, 2 factorial is 2. Here we have 15 divided by 8, right? 5 3s are 15, 2 times 2 times 2 is 8, and we have pi raised to 5 by 2, 2 times 8 divided by 15, right? So taking this 8 to the numerator. So we have 2 8 just 16. So we have 16 times pi raised to 5 by 2 divided by 15, right? So the value of this integral is equal to 16 over 15 times pi raised to 5 by 2. So viewers, this is how by the application of beta function we can evaluate these kind of integrals.